Yeah.
And I don't know if I ever told you, but soon after that, I went to London, England to give a seminar. And I brought the PowerPoint, but I also brought slides and I brought overhead transparencies. But when I got there, the computer thing didn't work. So I said, I'll use the slides. And I had set them up correctly in the room they gave me, but they started coming out upside down, every one. And I said, how could this be? And then the guy said, oh, the room you tested in, I forgot to tell you, there's a mirror that inverts them. So but then I went ahead and I then used the transparencies, and those worked, you know, but I brought power. Now I only bring the PowerPoint, but back then it wasn't such a sure technology, you know.
True. True.
Okay, so that you share your screen, so
can I do that?
Yes, you are allowed to do it, I think.
How do I? Okay, let me expand. Okay, now I got to do the sound.
Excellent.
Okay.
So you see my
Yes.
Yes.
Okay, then I'm.
It's my
and
pleasure.
some of you, it's like Louise, has heard this before, but I hope you're not exhausted.
No, I'm actually looking forward to. Yeah. That's
So it's my pleasure to finally introduce another time Dave Shapson. As I say a couple of times, he's professor at the Department of Cell and Molecular Biology, University of Hawaii at Manoa. And this talk is very special talk. I request Dave to give this talk at the end of all the lecture, because I think it deserves a special space during the workshop. He take a lot of care in order to prepare this presentation, and he has perhaps the unique characteristic to give this talk, giving the credit, not only because recognize the people who did the contribution along the time, but also to take care of the details. And I think he is the person to talk about nanohistory of fluorescence. So thank you very much, Dave. I will enjoy another time more of this lecture.
Okay, well, thank you very much. As some of you know, I've given this many times, and you know, once somebody said, why am I asked to do this? And I said, well, some people assume I do this because I've been around so long that I've seen everything that's happened in fluorescence. And I say, no. I said, you're thinking of Enrico, not me. But any rate, so I'm gonna give what I call my nano history. And I'm going to make some comments, a lot of comments actually, about the contributions of Gregorio Webber to this. And, it's not, why isn't it advancing when I hit my advance? Oh, okay, now it is. And there might be a few generally harmless remarks about Enrico along the way. Okay, so any rate, so the discovery and characterization of fluorescence. I gave a talk many years ago at a workshop in the Netherlands. And I said, when do you think fluorescence was discovered? And the students talked and said, oh, they think around the 1940s by this guy Forster. And I realized, well, it's not such a bad answer if they've never learned about the field. So I thought, well, older people like me should try to educate people about the history. So, but first I have to change your views on some things. So when was the first report on fluorescence? And I want to say that contrary to popular belief, it was not from the early ancestors of Dave and Enrico, okay? Because people sometimes think this, okay? But this is not the case, okay? Despite what people may think about that. Nor was it from Enrico's kitchen, another misconception for some reason. And I don't know why that is, but at any rate, forget that. Let's talk about the real history of fluorescence. And it's generally credited to Nicolas Monardes, a Spanish physician botanist who talked about the medicines of the New World. He didn't go there, but he read the reports of the conquistadors and others. And he's usually credited as the first to describe the bluish opalescence of water infusion from the wood of a small tree. And when made into cups and filled with water, a particular blue tinge was observed. Actually, I learned from Ulysses Zacunia that it was a Franciscan missionary, Bernardino de Sahagún, who actually went there to the New World, and he actually described this independent, and he said that the Aztecs called this coatli. So I think he should get really the credit for these early observations, but his work wasn't as well known as Monardus's. Now, an early translation by the influential Flemish botanist Charles de Lecluse, soon after that, gave the name of lignum nephriticum to the wood, which means kidney wood. And this helped to popularize the awareness of these optical properties in Europe. And the wood became very popular in Europe in the 16 and 1700s because of its medicinal values for treating kidney ailments. You know, it occurs to me that's particularly relevant to this workshop. We had several talks about kidneys and kidney ailments. So really this early work fits right in, you know. And an Englishman, John Frampton, translated Monardus' description as, and I quote, white wood which gives a blue color when placed in water that was good for them that doth not piss liberally, and for the pains of the rains of the stone. So you can see a nice description of early fluorescence right there, and kidney problems. But the first person who really did the nice work on this was Robert Boyle, the famous Boyle of gas laws, etc. And he was inspired by that work, and he discovered that after many, so he wrote about this, and he said after many infusions, the wood lost its power to give color to the water, and he concluded there was an essential salt in the wood responsible for the effect, which is an amazing thought right there. I think that something's being extracted from the wood. He also discovered an addition of acid abolished the color, stopped it, addition of alkali brought it back. And he actually wrote this. And so I like, Katie Reinhardt sent me an original copy of the 1670 manuscript, and you can read it. And he says, I found that according to my experiments, the colorless color immediately vanished when he added vinegar, acid. And then he says a few drops of oil of tartar del deliquium brought it back. And it took me a long time to discover that was potassium carbonate, what they called it back then in the 1600s. So Boyle was the first to use fluorescence as a pH indicator, and he really did. I've looked at other works of his now. I have several papers. And he would use the lignum nephriticum color to determine if some of his solutions were, we would say nowadays, were more acid or alkali. So that's pretty amazing. You would love what we do nowadays. But the identification and fluorescing molecule from lignum nephriticum wasn't discovered till 2009 by Ulysses Zacunia and his colleagues. And I actually have a picture of Ulysses Zacunia at the end of my talk, and you'll see why it fits in there. And this is from his paper. And he showed that there was he worked out the amazing chemistry of the change when you have an alkaline rearrangement of the starting material to the fluorescent material there. And that material, which they call natylene, really had a quantum yield of 1 and a lifetime 2.76. It was amazing to actually see the ancestral molecule. And in fact, when you put it in, and by the way, there will be a demonstration of this and some other stuff at the end. We couldn't arrange it right now, but at the end of the talk, Leonel is going to show some of this in the lab. But I remember in my lab, I got some of the wood from Ulysses Zacunia, and I had an alkaline solution in a hand lamp, and I dropped it in, and it lit up immediately. You can see the piece of wood there at the bottom. It's just amazing when you actually see it. And I found out more recently, or in 2018, now there's other works, people looking at other things, like one type of sycamore tree gives a wood which also gives fluorescence depending on the pH. So it's sort of a coumarin type compound there. But it's funny, I mean, after people became more aware of the fluorescence properties, I think after Ulysses' paper and some stuff I did, but you begin to see the people looking at other woods. So you don't necessarily have to get your hands on the lignum the friticum. You can get these other woods to do this. But to take a little break from fluorescence per se, I think it's important to see what Galileo did. And he described an emission from the famous Bologna stone discovered in 1603 by a Bologna shoemaker. And it was known that when you, this guy discovered when you put this in the sunlight during the day, then brought it in and heated it up at night, it gave off light. And I remember at the University of Illinois going across campus one day with Enrico to get the original Galileo manuscript, which Enrico translated and said, and I love this, it must be explained how it happens that the light is conceived into the stone and is given back after some time as in childbirth. But that already is an indication of thinking, well, there's some process, we know now it's the phosphorescence lifetime, and Galileo was so stupendous, he was already thinking about this. Now, who else was important in fluorescence? Well, David Brewster in 1833 already described you have an alcohol solution of leaves and you pass white light through it, you can see a red beam from the side. And of course, that's chlorophyll fluorescence. And chlorophyll fluorescence nowadays is very important in plant health and photosynthesis. And they have portable fluorescence things to go into the field to look at the chlorophyll fluorescence. But in fact, it's even out of this world now, because now they have satellites observing chlorophyll fluorescence from the satellite shining lasers down. And here's some maps, and I like this top one where you can see the chlorophyll in the red, the concentration in the Amazon, Central Africa, in the jungles of Vietnam, Cambodia, Laos. And any rate, it's interesting that people are looking at the health of some of these with satellites now monitoring the chlorophyll fluorescence. Well, a very, very, very important person for our field was John Herschel. And he was an amazing person, and I can't go into the details, but I read more and more about him. A mathematician, astronomer, chemist, experimental photographer, and inventor. And here's a picture he took of himself in 1867. So it was pretty amazing. And he actually named 7 moons of Saturn and 4 of the moons of Uranus, which was discovered, by the way, by his father, Sir William Herschel. In addition, he also translated the Iliad of Homer into English, and he invented blueprints while he was at it. So this guy was amazing. But for us, what was extremely important, in 1845, he made the first observation of fluorescence from quinine sulfate, which he termed epipolyc dispersion. And this is his paper on the case of superficial color presented by a homogeneous liquid internally colorless. And as he described, and I love the way they wrote back then, he said it gave an extremely vivid and beautiful celestial blue color. And there it is, tonic water, and you put a hand lamp up, and you can see the fluorescence. In fact, having said this, of course, you might think of gin and tonic, and Enrico tells me that many bars have UV illumination that permit one to observe the fluorescence from a gin and tonic. Now, naturally, I have no personal knowledge of this fact, but I believe Enrico, who I'm sure is much more knowledgeable of gin and tonics. But I wanted to mention for a minute, we can all realize the debt we owe to quinine. The more and more I realized as I did these lectures, it's probably the most important molecule in the development of the fluorescence field. Why is that? Well, let's talk about it first. Quinine is the bitter compound, comes from the bark of the cinchona tree. And this tree is most commonly found in South America, Central America, Caribbean, and parts of Africa. But by 1650, already shipments of cinchona bark were sent regularly from the New World back to Spain from its colonies for the treatment of malaria. They already discovered that it can be useful for treating malaria. In fact, in the 1600s, it was used around the Vatican too for that. And for more than 300 years, these trees were the only source of quinine, okay? And as we'll see, efforts to synthesize quinine eventually led to the development of the dye industry and synthesis of fluorescent molecules. But before we go into that, let's see some of the first work done on quinine by George Gabriel Stokes. And this guy absolutely has to be called the ultimate father of fluorescence, and I'll explain why. He had this wonderful paper in 1852, and of course I have a PDF, and anybody out there that wants a copy, send me an email and I will send you the PDF of Stokes' paper. It's 100 pages and it's wonderful to read. And he also described this, he was interested from Herschel's work as a beautiful celestial blue color. But the very important thing for us now, in this work, he initially used the term dispersive reflection to describe this phenomena, as other people had referred to it, by quinine sulfide. But then he wrote a footnote, which is vital for all of us here, okay? And the footnote said, and this is a clip from it, "I confess I do not like this term. I'm almost inclined to coin a word and call the appearance fluorescence from fluorspar, as the analogous term opalescence is derived from the name of a mineral." So if not for him, you would be having an advanced workshop in dispersive reflection applied to microscopy. So we have to, not only did he give the name to it, but he was the first one who really realized it's not just refraction or reflection of light like Newton thought it was. It's absorption and emission of light. That was Stokes that came up with that concept. And this was a beautiful experiment he did. He used a prism to disperse the solar spectrum to illuminate a solution of quinine. And he noticed that you saw no effect until the quinine went into the ultraviolet region of the spectrum. And he wrote this beautiful phrase, "It was certainly a curious sight to see the tube instantaneously lighted up when plunged into the invisible rays. It was literally darkness visible. Altogether, the phenomena had something of an unearthly appearance." So they knew how to write back then. But these observations led Stokes to proclaim that fluorescence is of longer wavelength than the exciting light, which led to this displacement being called the Stokes shift. The next important person in this area, I would say, was William Henry Perkin, who you can see he's famous in England. He gets a plaque where he worked. And we're showing the structure of this compound mauve that he developed. But how did he come across mauve, this purple pigment? Well, in fact, darn it. Every time I click on the wrong place, it goes to that. Okay, you have to click outside. Well, in 1856, at the age of 18, he set off with the idea, he was working for a chemist, the idea of making quinine. Again, why quinine? Because the British Empire was already everywhere and they were suffering from malaria. And so there was an interest to get quinine, so you didn't have to get the darn bark from the New World. And he oxidized allyl-toluidine from coal tar, and instead he came up with mauve. And fortunately for him, what really kicked it off, Queen Victoria loved this color. So he started a company to produce dyes, and next produced a green and a violet. And they say that the canal outside his factory turned a different color every week. And although some others had synthesized synthetic dyes around the same time, Perkin was by far the first to recognize the potential for commercialization. It really started the synthetic dye industry. And histologists were already using this within a decade. And this is also interesting. He also, like Herschel, was an amateur photographer, and he took a picture of himself at age 14. I don't even have a picture of myself at age 14, but Perkin has his. So who's the next important person along the line? Well, I would say that's Adolf Onber, who ultimately gave rise to the Bayer company, a German chemist. And he synthesized this compound. And I guess I don't have to tell you what that was. Okay, maybe I do have to tell you. Fluorescein, all right? And he synthesized that in 1871. And Why did he call it fluorescein? I often wondered that, and after a day of library work, I discovered from his early papers, he apparently coined the name fluorescein from flow for fluorescence from Stokes' stuff, and racine, which is German for resorcinol, because he reacted resorcinol with phthalic anhydride to give rise to fluorescein. And so the name actually tells you the synthetic route he took. And in 1905, he got the Nobel Prize in Chemistry for all his work. So he was the first fluorescence person, let's say, that was recognized for this stuff. So, but already in 1877, already 6 years after von Baer made this, they used fluorescein in a major groundwater tracing experiment in southern Germany. This paper by Knopp, and Oliver Holub, who used to work with Enrico, translated this for me. And they took 10 kilograms of fluorescein and added it to the Danube on Tuesday, October 9th, 1877 at 4 o'clock in the evening. I love the detail, but it's important because now we quote, the effect of the same in the spring of the Ock, I show the stream of the Ock to the right, was detected on Friday, the 12th of October at daybreak, thus about 60 hours after the completed conduction of the experiment. And they said the water in the Ock in the spring was splendiferously green lucent for 36 hours. So the result of this experiment showed that the Danube and the Rhine rivers were connected by underground streams, and they still use fluorescent molecules for some of these water tracing experiments. Now, you may think, oh, that's terrible, putting 10 kilograms of fluorescein in the river. What about the environmental protection agencies? Well, fluorescein is one of the few things that's so water soluble, it'll go right through your body, that St. Patrick's Day, the Chicago River is dyed green with 40 pounds of fluorescein. Well, now they use, the last couple of years, a new dye, but proprietary. But that's basically it. Okay, and I want to give now to show you what I call the opposite of a single molecule experiment. You see the fluorescein being thrown over the back of the boat.
C'est clair que ça prend méchamment le laser. Je pensais que ça allait être des zones, mais pédale. C'est vraiment du vrai produit chimique.
All right, so there's fluorescein. But it's interesting to note that in 1897, and rhodamine was made by Maurice Ceresol in a patent. Now, he worked for BASF, a big German company, and he worked with Heinrich Caro, who trained with von Baer. And so Heinrich Caro thought, well, we need to make more of these dyes. And he gave this job to Ceresol, and he made a series of red dyes, the rhodamines, and he called them rhodamine from the Greek rhodon, meaning rose, and they were amines, they were basic, and he synthesized a series of them, like rhodamine B, rhodamine 6G, rhodamine 3G, and others. And it's interesting, there's a whole series of papers in this journal, Biotechnique and Histochemistry by Cooksey, where he gives quirks of nomenclatures for many of these probes. So this came from Cooksey's things, but it's a wonderful series of articles on nomenclature. Already, Paul Ehrlich used urine and a sodium salt of fluorescein to track secretions in the aqueous humor in the eye, first in vivo use. And many of you have been to the ophthalmologist where they put a drop of a yellow thing in your eye, that's fluorescein, and then they shine a blue light and they can look at the green, which looks for it can see things in the cornea and everything, if everything looks healthy. And Nowak already in 1887 already published a book listing 660 compounds according to the color of their fluorescence. That, of course, was the earliest example of the molecular probe catalog I mentioned already. Mayer described the term fluorophore to indicate chemical groups making something fluorescent, like chromophore from Witt did. And Heimstedt and Lehmann independently developed the first fluorescence microscopes as an outgrowth of the UV microscope. Okay, so this goes back quite a ways. One of the heroes in this early work was Stanislav von Provosek, who in 1914 published this paper on the fluorescence of cells, where he used a fluorescent microscope to study dye binding in the living cells. And he was doing this to study typhus, because typhoid epidemics were there. And he died of typhus that next year, actually. And I already mentioned Albert Kuhn's making fluorescein isocyanate and Riggs making FITC. And I mentioned Gregorio Webber synthesizing the danzo proteins to attach to proteins. And I mentioned Shimmer Mirror, who discovered green fluorescent proteins in the jellyfish. But I want to say something else about Shimmer Mirror, which is interesting. As I mentioned, this is in the outer ring of the jellyfish. And he said in this paper, when he was later describing the search for this, how to get this, he had to purify 70 milligrams. It took him 30,000 jellyfish, weighing 1.5 tons. And I doubt if many of you would be using fluorescent proteins today if you had to purify it from 1.5 tons of material. In fact, he said his hands got so tired cutting the rings out that he developed this ring cutting machine he describes, where he would flatten the jellyfish and cut the ring. So boy, this guy deserved the Nobel Prize for this work. Now, let's switch to some other techniques. Polarization, which as I mentioned is very important in fluorescence. And probably the first use of polarizers, although they didn't call them that, of course, were the Vikings. They had this sunstone, which now we think was probably isonspar or calcite, which are naturally polarizing. They would look at the sky in these overcast days, which are always overcast, let's face it, up in the winter up where the Vikings were at, and they would rotate it. And because scattered light was strongly polarized, they could see the direction of the sun and navigate, which was important as they went around to pillage and destroy villages around the world. So polarizers helped them in this job. But the first one to use the term was 1808 was Etienne Louis Malou in Paris. He observed sunlight reflecting from the windows of the Luxembourg Palace in Paris using this calcite crystal he rotated. And he saw that the intensity of the light varied as he rotated the crystal. And he coined the term polarized, describe this property of light. And he published this in a paper in 1809. And it's interesting because he even came up with this rule. He would cross two polarizers, that the intensity of the light passing through two of them depended on the cosine squared of the angle. So I think it's interesting that he recognized that already in 1809. But we owe a debt to David Brewster because he was studying refractive index and the angle of incidence on polarization, and that was in this paper on the law of partial polarization of light by reflection. And he discovered that at about 56 degrees, you get total reflection in Brewster's angle, which you've heard about in the course. But he used that to construct a pile of plates polarizer. You take a series of glass plates and you arrange them. And the second arrangement on the bottom is nice because if you arrange them that way in alternate orientations, you can keep the light in the same plane as it goes through. And these were used for people for many, many years. In fact, if you look at the original thesis of Gregorio Webber, in his thesis, where he's doing a lot of polarization, he describes this pile of plate polarizer that he had. And both Enrico and I in Gregorio Webber's lab, he would show us his pile of plates polarizer. And it's tragic that we no longer know what happens to it. It was a great device that he used in his day. And William Nicol, however, discovered that when you join two crystals of isonspar at this angle of 62 degrees, you could get polarized light to come out of them, and this made the famous crystal polarizers. And nowadays, there's many calcite polarizers used. I showed one when I gave my first talk. We have Glan-Foucault, Glan-Thompson, Glan-Taylor, Wollaston, but lots of crystal polarizers. However, the Henry Ford of polarizers, meaning the guy that made it available to everybody, polarizers, was probably Edwin Land of the Land camera fame. I mean, he started that Kodak company. But in 1929, he, as an undergraduate at Harvard, he dropped out to patent the sheet polarizer, the J sheet, where he learned by embedding iodoquinine sulfate in nitrocellulose film and stretching them, you could generate a film that would work as a polarizer. And there he is holding up some of his original thing. And this made it much, much cheaper for everybody to play with. Now, I just want to mention a very, very important paper on polarization energy transfer by Gabriel, the famous guy who did the lifetime. We'll talk about him again. In 1924, and he showed that when you have a very, very concentrated solution of sodium fluorescein, urinin, and you look at the polarization in glycerol, you get zero polarization at first. And it's because it's so concentrated, so close, you can energy transfer between the fluorescein molecules, which depolarizes the emission. But he didn't know what was going on then. But then as you dilute it and dilute it and dilute it to something like 1/20,000, you climb up to 0.45, the limiting polarization. It was this work, as we'll see, that helped inspire many people, including Francis Perrin, to investigate this phenomena, which he realized had to do to energy transfer. This was very important in the field of energy transfer. So let's talk about Francis Perrin, who was the son of the famous physicist Jean Perrin. And you learned a lot about translational diffusion, certainly from Enrico's original lecture in the course. But his son, Francis Perrin, was famous for rotational diffusion. And it's funny, it must have been when Francis Perrin was growing up, he said, well, Dad did translation, what's left for me? Well, I'll do rotation. So that's what he did. There's a good discussion of his life in an article by Mario Barberon Santos. But in 25 to 26, as I mentioned, he published important papers giving a quantitative theory of fluorescence polarization, including the classic paper. And here's his original Perrin equation that I simplified for you before. And as I said, this was largely in the province of physicists for 2 decades until Gregorio Webber did his thesis work. But first, before we go to Webber's work, let's first talk the Timeresolved. And I showed this picture before, and I said how R.W. Wood made the first attempt to measure the lifetime, as you see from this article. And he did a method which I thought was so clever, it's just amazing. Unfortunately, it didn't work, but you have to give him credit for the method. And he worked with this guy, University of Wisconsin, Professor Mendenhall, and they got a high-pressure pump to shoot out a jet of fluorescent dye. They used different dyes, but let's look at anthracene was one of them. And they would get it going out at 230 meters a second through a tiny nozzle. And they scraped the black material off the nozzle so they could shine light right through it. And then the idea was, well, by looking at the length of the fluorescence in this flow, they'll get the fluorescence lifetime, which was great when you think about it. Wow. Unfortunately, it didn't work. They said we could measure durations less than 1/2,300,000 per second, which is less than 435 nanoseconds, but they didn't see it. Well, that's because it was a shorter lifetime. But thanks to the work of Wood, it put an order of magnitude on fluorescence lifetimes. It was less than this. And actually, more recently, 2013, and even today, I like this paper by these guys who made a flow chamber where they're flowing dyes of terbium and europium, which gives long-lived fluorescence on the order of micro to milliseconds. And they can actually observe in the image what Wood was trying to see and get the lifetime basically by plotting the image versus distance or time in here. So people went back to this idea. But it was the famous physicist Enrique Gabrieli who first made the fluorometer. I told you that's why it's lifetime. Instruments are called fluorometers. Spectrum are called fluorimeters. And he built this already in Berlin, where he was working in 27. And he was one of the most outstanding scientists produced in Argentina in all of its history. And we won't go into the details, but when you look at the professors he had, Frank, Hilbert, Perrot, Born, Planck, Einstein, Nernst. I mean, boy, that was a tough professors and a tough thesis committee. So, and he did a lot of famous work. And he was the first one to measure by his lifetimes, okay? And I won't go into the details of the instrument, but for sodium fluorescein, he got 4.5, which is pretty good. For rhodamine, he got 2 nanoseconds, which is right on what we measured today. So he did the first accurate measurements. Now, what about lifetime microscopes? Well, it's not a recent invention. Already in 1955, 59, Boneta in this paper described an instrument where he says in the paper how he got all these parts from TV sets and whatnot. And he was able to get a lifetime. He looked at lifetime of proflavin, I think, in the nuclei of tumor cells and some autofluorescence. He wasn't doing imaging, but just of the whole cell. But he was able to do some measurements. And so he first was doing this work. Now, this sentence appears in the 2006 books that 50 years ago, Forster found 2 fluorochromophores in close proximity changed their properties. That's not true. I mean, Forster did a lot of great work, but he didn't discover it. Cario and Frank first discovered you could excite a mixture of mercury and thallium atomic vapors at 254 and see the emission at 535 from the thallium, although you excited mercury, meaning there's some transfer of energy. And wow, oh, once again, you see, darn it, I clicked on the, I clicked on the wrong place. Gabriel and Pringzheim did that polarization thing I told you. Jean Perrin first proposed a mechanism of resonance energy transfer, and then Kalman in London did a quantum theory work on this, and Francis Perrin published a quantum mechanical theory, and he did everything except the effect of the overlap integral. And Tay Forster came and wrote the first complete theory. So yes, Forster did extremely important work, but he was standing too on the shoulders of other people in the area. And Forster is recognized for his important work. And I think it's interesting. There was the first International Theodore Forster lecture series that came out. And the first lecture was Enrico Gattone at that in 2007. It looks, however, like he's talking about particle tracking at the Forster thing, but I'm sure he worked energy transfer in there somewhere. I don't know. We'll have to ask him. But the origins of the first commercial instruments, which really led to a boom of the use of fluorescence in the field, came because of the anti-malarial research in the 40s. During World War II, the government issued a call to scientists to develop better treatments for malaria due to a shortage in quinine. Again, quinine, you see how important it was. And researchers at the NIH were trying to develop fluorescence assays, but they didn't have good instruments. And then finally, Robert Bowman, in the Laboratory of Technical Development at the NIH, developed the first flexible instrument. And that led to the first commercial spectrophlorimeters with monochrometers for excitation and emission, produced with the American Instrument Company, which was located close to the NIH, Amico, and so it was marketed as the Amico Bowman. And many of us old timers have actually seen these early instruments, which really helped to popularize and made it available to so many people. Well, because in 1956 this came out, and this is the original brochure, the cost was $8,000. You'd say, well, I can buy that for my allowance. But back in 1956, that's about $100,000 in 2017 dollars. So let's go forward a bit. Fluorescence in the 20th century. As I said, most of the basic principles were developed. Gabriel did the lifetime, Vavilov, the quantum mute polarization, Weigert observed it, and Perrin quantified it. Energy transfer, Jean and Francis Perrin, Tay Forster. But until the second half, fluorescence in biology and biochemistry was descriptive in nature, used usually as a role in isolation, purification, quantification, such as using compounds like riboflavin and porphyrins. And true quantitative work relied on Gregorio Webber. So let's talk now about seminal contributions of Gregorio Webber, because a few of us were lucky enough to have known him and worked with him, and many of you did not. But during the last few decades, it became very important. And certainly one individual, Webber, is singled out for his outstanding contributions. So let's have a bibliographic sketch. Well, he was born in 1916 in Buenos Aires, Argentina, on July 4th. Even today in the United States, we celebrate his birthday with fireworks, but that's another story. And there's a picture of him at 1 year old, courtesy of Francisco Barrantes. How he got a hold of this, Lord only knows. And Webber did an MD degree in University of Buenos Aires, and I asked him why he did an MD, and he said, well, he loves science, and he told his high school science teacher he wanted to be a scientist, and this high school teacher in Argentina advised him, that's good, but it's not always easy to make a living as a scientist in Argentina, and you should become an ND, because then if it doesn't work out as a scientist, you have your medical career to fall back on. Fortunately for all of us, it worked out for him. But it's important to know he was an assistant with Bernardo Husset, who was awarded the 1947 Nobel Prize, the first Argentine and Latin American to get a Nobel Prize. And in fact, he recommended that Webber apply for a British Council fellowship, which were very difficult to get back then. Only a couple of the world were given out. And Webber got it to go to Cambridge to work with Malcolm Dixon, and we'll see that in a moment. And he got a thesis there, and he continued to work in Cambridge until 1952. Then he went to Sheffield in 53, and in 62 went to the University of Illinois, where he stayed the rest of his life. So as I said, Bernardo Husset encouraged Webber, and there he is back then in 43, to go to England. And Webber told me that that was during the war, and they had to go in a convoy. It took 44 days in a convoy to go to England. And I heard the story of that convoy many times, and each time he told me the story, I swear there were more and more U-boat attacks on the convoy. And here we see him going, and there are U-boats occasionally. Oh, there, you see? Okay, I think you saw one there. But he survived, and he got to England, and then he started to work with Malcolm Dixon. Now, the old timers remember Malcolm Dixon was the world's preeminent physical biochemist at the time and the leading authority in enzymes. In fact, he recorded the first absorption spectrum of cytochrome C. You can see the influence on Webber being interested in spectroscopy. And he suggested that Webber consider applying fluorescence techniques to study naturally fluorescent flavin and flavor protein systems. Well, as Webber said, he knew little about it at the time. He knew there were some low molecular weight compounds, riboflavin, FAD, that had fluorescence of different intensities, but only a few flavor proteins were purified. So he was given the task of sorting out this area. He thought it would take a couple of years, and of course, he worked the rest of his life. Now, here's his thesis, front page, fluorescence of riboflavin diaphorase, which is flavin binding proteins related enzymes. And here he is getting his PhD, graduating in St. John's College in Cambridge in 47. And I want to mention something, the final chapter of his thesis, because this has come up in the course. It's devoted to application of polarization measurements to determine viscosity of gels. And he actually wrote this in the final paragraph. So he talked about the micro and the macro viscosity are of importance. And he realized the difference. And he told me personally, he realized that when he had gelatin and he put fluorescein in, and you could bounce the gelatin in your hand, but the polarization was near zero, like in water. That's because fluorescein was in water pockets between the gel fibers. But rhodamine would bind to the gel fibers, and you would measure a very high polarization. And that gave him this idea, and he talked about doing this in cells and cytoplasm and whatnot. And that observation anticipated the work he published 24 years later when he first delineated the application of probes to study physical states of lipids. And I told you about that work he did with Perlin and Mayer-Shininsky and all of that stuff. But that anticipated, too, the very important work done today, which this has expanded a lot. I think I got this slide years ago from Louise Bagakoli, so thanks again, Louise, with Lordan. And of course, now you've seen how important these type of studies are. But before designing probes, though, he carried out independent investigations. I'm saying in terms of this theme designing probes, but he wanted to study methods to allow him to study proteins that did not contain intrinsic fluorophore, because intrinsic fluorescence of proteins had not yet been discovered, which he will do, of course. So he put a lot of time and effort, he said 2 years, to come up with a probe, danzo chloride, which is still used today, that he could use with the instrumentation available then and attach to proteins. And so with this, he began to look at several protein systems, and he had 2 famous papers, a lot of citations on theory and then observations. It's interesting, the theory paper has an acknowledgement to Francis Perrin for his suggestions. I wish I had thought to ask him when I had a chance, what were the suggestions Perrin gave you? But he extended Perrin's theory to the case of ellipsoidal molecules carrying randomly oriented oscillators. Now, I want to show you some pages from that theory paper, because I think some people think, well, big deal. So he had the Perrin equation, fine. It was a really difficult paper at that time. And I'm just going to click through 6 pages, just glance at them as I go through it. This may inspire some of the mathematically oriented among you to look at these papers. So this was his first paper on polarization. As you can see, this is not a trivial work. In subsequent years, he continued to advance the theory of polarization. And this was done already in 73. But then later on in the second paper, in the second paper, it's a re-examination of several treatments. In fact, I think that paper was a little later than that, where it's the final, everybody agrees on the final papers, what everybody did for anisotropy decay, time-resolved polarization. So this was the final one. And now to go back to his early career, in 53, he was recruited by Hans Krebs to go to Sheffield, the biochemistry department at Sheffield. And as you know, Krebs is the guy got the Nobel Prize for the tricarboxylic acid cycle. And during his years at Sheffield, he continued to lay the foundations of modern fluorescence. And here's a picture of the Nobel Prize celebration dinner when Krebs got the Nobel Prize. And there's Gregorio Webber and there's Krebs at the dinner. So that's interesting to see that. And one of his pioneering contributions was his report with David Lawrence on the fluorescence properties of anilyl naphthalene sulfonate, where he pointed out that in water is very weakly fluorescent, but in the presence of a protein or a nonpolar solvent, the fluorescence greatly increases. And after this, Leonel will do a demonstration to show you. It's a beautiful demonstration, easily done for all of your students. And it's still used today, ANS. Now, I've added to this lecture something I didn't have in my previous history lectures, because I thought what an idiot I am. So much talk in our lectures during this course on NADH, NADH, NADH. Well, who do you think first described the fluorescence of NADH? Of course, it was Gregorio Webber. And already in 1957, he described intramolecular energy transfer in the ring system of NADH. But what I want to bring your attention to, this is 57, long before he had the capability to measure a lifetime. So then he talks about dihydrophosphorypyridine nucleotide. That's what they call NADH for a long time. And here he talks about calculating the lifetime from the polarization, and he comes up with 0.5 nanoseconds. All right, so remember that. His next paper on this topic was 1958, which was a very complete paper. As you see, it's 8 pages long on all the fluorescence properties. And this was it's all written in French. I told you he could speak French. In the French journal, Journal Chimique Physique. And again, NADH. And in here, you get to the end, it's interesting because he uses the equation, as he says here, the Forster equations to calculate the lifetime of NADH from the basic absorption and properties of it. Now, this was done, Forster's equation was 1951. It's interesting because in 1960, after this paper, Strickler and Berg came out with a more complete and more accurate formula. But already during this, so he's calculating the lifetime in this paper, and he comes out with 0.34 nanoseconds. So I thought it was very interesting to look at his average lifetimes, 1957, 1958, without measuring any lifetime, etc. He comes out with 0.42. And I would say that was pretty darn accurate according to the phasor plots we've seen during this course. So they knew what they were doing back then. But very, very importantly then too, with his postdoc, John Thiel, he did the first studies of the aromatic amino acids of proteins. So they published a series of papers where they did the first description of the excitation and fluorescence spectrum of the aromatic amino acids. And they had this famous paper, and figure 7 from this paper has been reproduced many times in many reviews. And that's figure 7 in the lower right down here. And in that paper, he did very careful excitation and emission. It was very difficult back in those days to do these measurements. They were done in 56. But at any rate, that plot in the bottom right has been used many times. And I'm particularly proud of more recent use of it. Namely, I've been involved for a few years with NASA on our Europa project, where they plan to send a probe to Europa to land on the moon of one of the moons of Jupiter, Europa, and look for different things such as biomolecules. And I insisted, well, they want it like tryptophan, I said. And I said, well, you have to use this figure from Gregorio Webber, and they did in their official description. So there, Gregorio Webber was very proud to see a description of his work involved with the modern Europa project. And there it is. So I'm very pleased with that. Well, he continued to design probes all of his life. And he made bis ANS, which is a dimer of ANS, which turns out to bind strongly to nucleotide binding proteins. He designed IEDAS, which is the very first sulfhydroreactive probe, so you can react with cysteines. He designs pyributyric acid, the first long lifetime probes to attach to proteins, but would have a long lifetime. And of course, you've heard many times here the famous series of probes, Loredan, Prodan, and DACA, and he studied each of them. And I use this picture on the cover of my book, Introduction to Fluorescence, taking Loredan at -80 in glycerol and Loredan at room temperature, and you see the beautiful change in the color due to the relaxation of glycerodipose around it. And as it's been mentioned before, it was Faye Ferris, his technician, that made this with him. But this is the actual lab they made it in. And this lab would put the fear of God in the health and safety people nowadays. And those of us working in Webber's lab, we were fearful to even go into this lab. It just looks so, from a health standard, you were a little leery of this. But that's where all these probes came from, that lab. That's where Loredan started. So phase fluorometry, we're already in the 50s, he started to think about constructing a lifetime machine. And of course, he said he was influenced by the work of a fellow Argentinian, Gabriel. So he wanted to work on a phase fluorometer. At that time, Burks and others had built some phase fluorometry. But in Illinois, with his student Richard Spencer, they constructed the first highly versatile phase and modulation fluorometers using the principle of cross correlation. I won't go into that, but this cross correlation approach is still used today. It's the key to modern phase fluorometry and is universally used. And here's a picture from back then, before my time there. Richard Spencer, who built that, and Gregorio Webber. And if Susanna's there, she might recognize, or no, that's Anna Jonas, who became well known in lipoproteins later. But again, we said that he had this machine, and of course he measured NADH with this, and he got 0.38 nanoseconds. So again, all these measurements were done, 5 decades before the rest of us, okay? So it really was something. So modern phase and modulation fluorometry began when Enrico Gabrieli joined Webber's laboratory as a postdoc in 75, 76. And this is the famous picture of Enrico talking to Gregorio Webber as they walk across the quad, the mall in the University of Illinois campus. And as he said, at the suggestion of Webber, he worked on developing a phase and modulation fluorometer, or continuously variable frequency instrument. And he returned in 78 as assistant professor. Enrico did, but by then he finished the first true multi-frequency phase and modulation fluorometer using a Paco cell, completing Webber's vision. And this shows the original instrument layout of Gabriel. This was Webber's thing, where they used this famous Dubai Sears tank modulate the light. Enrico's first Paco cell machine in 1983, and now many, many different types of FLIM microscopes are available. And Webber's work on phase and modulation fluorometry also, as I mentioned before, indirectly led to development of the phaser approach by Enrico. Awards. Well, Webber got a lot of awards in his life. American Academy of Arts and Sciences. I'm going to talk about some of these in more detail. The first national lecture. Many of you go to biophysics, I think, or know about it. And every year since 1969, they have a national lecturer, a big shot in the field of biophysics. Well, the very first one was Gregorio Webber. Guggenheim, National Academy of Argentina, National Academy of the United States, the Rumford Premium, I'll come back to in a moment, ISCO Award, Replicant Award, I'm going to come back to in a moment, and the Blonsky Award. Now, Webber told me his favorite award he got was the Rumford Premium, and this is because it's the oldest prize in the U.S., given out every few years since 1839, set up by a bequest from Count Rumford. Webber got it this year for his work on fluorescence. It's in fields of light and heat. And these guys sharing it with him are Mills and Yang. And Yang got the Nobel Prize for work on gravitational theory. I'm not sure where that fit in, but Webber sharing the prize with these guys. And he said it was really nice to be on the list of other people who got it, like J. Willard Gibbs, Edison, Wood, Michelson, Bridgman, Lant, Fermi, Onsinger, Towns. So Webber said that's not a bad group to be included in. I guess not. And also the replicant. Well, in 1985, the American Chemical Society started their Replicant Award for chemistry of biological processes. And they gave it out to Webber, was the first one to get it, for his work on proteins. Again, I could give an entire lecture about Gregorio Webber's contributions to proteins, but I'm focusing on the dynamics. But he did the fluorescence to study proteins, and that's another story. And we've had a lot of international symposia honoring Gregorio Webber. The first one we had, which Enrico and I organized, was in Bocca di Magra, Italy. And here we see Gregorio Webber. Here's Enrico. Here's me. And there's Ulysses Zacunia. I told you I had a picture of him, the lignin friticum guy. And I only noticed recently, there's this guy at the corner. That's Jim Longworth. That was Gregorio Webber's first PhD student, believe it or not. So it's kind of nice to see, and a lot of other fluorescence people in the field. I won't name them all. And we've had a series of these Webber symposia, 10 of them, in fact. We had them in Italy, then we switched to Hawaii, Maui, and then to Kauai, and then we switched to Brazil, Buzios. Well, we see the Kauai meeting. Here's some of the speakers there, a typical day at the Kauai Webber meeting. Buzios was another great place to have a meeting. But I wanted to emphasize these meetings really are known for their total focus on the rigorous science. I don't want you to get the wrong idea looking at those locations, okay? And here we see Enrico demonstrating fluctuations in person at one of the Webber meetings. And also Enrico gave a hands-on course on diffusion and particle tracking, which many people participated in this hands-on course. But that's another story, okay. The 11th Webber Symposium, we weren't able to hold it due to the pandemic this year. And we weren't going to have it in Brazil, but that's out of the question. So we hope maybe we can have it in January 2022, but we have not picked the location yet. Who knows? Uruguay may be in the running, but time will tell what happens there. And if you go to the LFD, there's web pages about Gregorio Webber, and there was this book I helped to edit with many people wrote chapters in 2016 about, which is the 100th anniversary of Gregorio Webber. And Pacho Barantes is a beautiful thing about Webber's roots in Argentina. Enrico has a talk and lectures and other people talking about Webber. And I have on my website things about Gregorio Webber. I also, anyway, we won't go into that, but there was a nice tribute to Gregorio Webber website done by David Lloyd, who was an undergraduate with Gregorio Webber at Sheffield. And he got a lot of the old timers to write little tidbits, and there's a lot of them there, and you can see that website. And I wanted to just mention one by Fred Sanger. Many of you know Fred Sanger's won 2 Nobel Prizes in chemistry, in 1958 for protein sequencing, 1980 for DNA sequencing. So he had quite a career. And he knew Webber because Webber was down the lab bench from him, as he would say. And he said, I don't feel able to comment on his scientific work, it was in a different field, but I believe his contributions to science was more than we see in print. And I like this. During the time we were both working in Cambridge Biochemical Laboratory, he would frequently come over to my bench to see what I was doing, discuss my work, and make useful suggestions. I found this stimulating and often helpful to my work, because Gregorio had a considerable wider knowledge of science than I did and was a wonderful person. And that's a pretty nice statement coming from Fred Sanger. And I end with this. Some of you have seen this before, but for those of you who haven't, let me say, this is really an actual conversation that took place between me and Gregorio Webber when we were in Hawaii. And as you see, I've barely changed since those days. And there we are with Webber. And Webber said to me, you know, David, when I was much younger, an older colleague said to me, Gregorio, when you pass the age of 60, you will begin to notice that your students have more ideas than you and better ideas than you. And I said, gee, really, Professor? And then he turned to me and he looked at me for what I can only say was an alarmingly long time before he said, I have not found this to be the case. So that was his statement. But I've thought in recent years, now that both Enrico and I have reached this August age category, I wondered what would happen if he would have asked Enrico and I this question. So I imagine, suppose Enrico had been there and he said, how about you, Enrico? And I imagine what Enrico would say, probably say in their dreams. And I imagine what I would say. Oh, huh? Okay, so that's it. I'm done, and that's my final slide, Lionel. The talk is over.
Fantastic, Dave. As usual, I every time show more and more this talk, and you add these little details about the NADH that I didn't know, and it's unbelievable, the contribution.
Well, imagine he was measuring this. He predicted it to be around 0.4 nanoseconds without measuring it. And then he measured it and got around 0.4 nanoseconds. So
Fantastic.
That's something to think about, you know?
Yeah.
So we need to always include that in these lectures.
Unbelievable. So if you want, we can proceed for our experiment. I will become your lovely assistant.
Lovely assistant. Excellent.
We will need to turn on the light.
Let me stop my share.
Yeah, great.
Thank you for Louise, and thank you. And Enrico can add to many of these stories about Webber are absolutely true, as he knows personally.
I don't know how you have configured your screen, but I recommend you to have only the screen that we will be sharing, so you will not miss the experiment.
Okay. How do we do that? Oh, we go.
Give me a second.
Go to the room.
Yeah, give me.
We have to. How do we admit into?
This is just for setting up.
Okay. We're not going into the room yet. And of course, it's much easier in Enrico's advanced workshops. We do this in the lab, and Enrico is my lovely assistant. But Unfortunately, he can't be this time.
Okay, this is just for testing, Dave.
But everybody, oh, so you're not letting people in the room yet, or you are?
No, all the people is watching. All the people is watching. So we are ready.
So can you expand? How do I expand the screen?
Okay, you have to basically select in your presentation that you want to see the full screen without any other.
Well, how do I do that?
Okay, you have to go to the top and say full screen in the at the corner.
Ah, okay. I say full screen and I don't see it yet, but maybe it'll come up.
But are you watching at the bottle?
No, it doesn't matter if I can see it so well.
But can anybody tell me that you are watching?
Anybody else see it?
Lionel, under full screen, whoever's speaking shows up. So if there's no sound from Sala dos.
Okay, give me just 1 second. I know what I have to do. I have to share the screen from this. Okay. So how I should do this? No. How about now?
I just see the speakers.
Oh.
Maybe you should go to you being the speaker and then you can share your screen. Oh,
Yes, we can see now Sala dos.
really? I don't. How do you see it?
Dave, on the top right, you see a little icon called view.
Yeah?
Click on that and select
Speaker
full.
view?
Yes.
Okay. So
But now I only see
how about now?
Shell on my screen.
How about now?
Okay, now I see it.
Okay.
I see totally dark, but I see there's a bottle there, so good.
But this is just for testing. This is
Yeah.
a bottle of tonica.
Tonic water, so why not? Wow, that's too bright. Yeah, okay, that's better.
Okay. This is just for testing. I have my hand on front.
Okay, it works.
Okay, the next thing is what do you want to go for the neon friticum or for the?
Let's try the lignin friticum because historically that was the next one.
Okay. So this is a piece of wood with the neon friticum, and you will.
And that's an alkaline solution, right?
So basically, you may see that does not fluoresce, basically, right?
Yeah.
Now I will drop.
The wood's in. Okay, wow.
Can you see now?
Yeah.
I think it's too intense, the laser, but you may see now that there are.
Well, you get the idea. If you put other wood in there, you won't see that unless it's fluorescent wood. Excellent.
Okay, and let's go for the last one.
This is the ANS in water and then ANS. So that's ANS there? Wow.
ANS alone.
So that should have a very weak yellow fluorescence.
Exactly. And I will drop a solution of BSA.
Okay, can we see the yellow fluorescence first of the?
Yeah.
Oh, you can sort of see a little yellow there. Okay.
Okay. Here you go.
Yeah, here we go. Wow. Okay. And that was only BSA. You didn't add ANS. Everybody understands, right? And that's when we do this in person, everybody says, ooh, ah, it's great. Yeah. So you can unmute everybody so they can go ooh and ah.
I will do it.
People are still muted, huh? I think they're still.
Okay, I think I allow all to unmute, but anyway.
Well, I'm the only one unmuted, so that's okay. I'm the only one who can talk. It's going to be a very short discussion if I'm the only one talking here.
Okay. Everyone's typing ooh, ah in the chat.
Well, in the chat, but nobody's talking, so, okay. But I think if you want a discussion, you know,
Ooh. Oh, wow.
Okay, great. Great. Give me a second. So can you hear me?
Yes. I think everybody can unmute themselves now. I could.
Okay, great. So we reached.
So now we can all go, ooh.
Fantastic.
Oh. Ooh.
Fantastic. Okay, we reached the end, and I will pass some messages for tomorrow, and then I need some time for acknowledgement. So first of all, I would like to say that tomorrow morning, for those of you who would like to be on the breakout room with the topics that we pick in order to discuss in more detail, we will meet as every day, for example, I don't know, 15 minutes before 10, so we can split. We already have the people in the group, so we will split in 6 groups. We will have a first row, and then you will have the chance to pick a second breakout room to have a different discussion. Then in the afternoon, we will have the practical session within the 20 students that we have picked. And I will email you, all of you, perhaps today night, after we test if we will have 2 Zoom sessions or if we will do basically 1 breakout room. So saying that, I will proceed to the acknowledgement, and I would like to do this today because I'm not so sure if all the people will be tomorrow, and I think it's worth to acknowledge the people who spend a lot of energy and provide me a lot of support for the organization of the workshop. So first of all, I want to acknowledge to all the people who work with me at the Advanced Bioimaging Unit. This is a share or a joint effort between the Universidad de la República and the Instituto Pasteur that we are having here in Uruguay. We are putting together some new instrumentation here in the country. As I say in the first talk that I give, we are setting up 2 kind of multiphoton microscope with film and with FCS, with most of the technique that we have learned during the workshop. And this on top of the instrumentation that we already have here as a several confocal microscope, as also some instrumentation that I brought from California based on fiber optics and lifetime measurement and so on. So I would like to thank Marcela Diaz, Ana Laura Suárez, María José García, and Tabaré de los Campos, all of them members of the Advanced Bioimaging Unit. They were here all the time, behind the scenes, working with me, helping me with the breakout room, with the assignment, with the organization of everything. I also would like to thanks to the Instituto Pasteur staff, in particular to Natalia Lopez, Gabriel Lejano, Ariel Chaparro, and Daniela Hirschfield. They have been working with us in the last 2 or 3 weeks very, very hard in order to organize all this Zoom section, how to set up everything here. I will show just, let me turn on my camera because you will see how this works here, but we have basically several computers, and this is the screen that we have here, and all the cameras in order to have, I don't know, good quality for the presentations and everything. As well for the communication and all the social media and everything. Then I would like to acknowledge to the 2 institutions involved here, in particular the Universidad de la República. I am associate professor of the Universidad de la República, as well as principal investigator here in the Instituto Pasteur in the Advanced Bioimaging Unit. As I say, this is a joint unit between the 2 institutions. And finally, I would like to thanks to all the instructors. I am very proud of this that I show the first day, and I would like to show it again because really made me very, very proud. Are you watching now of this or not? No, sorry, because I have to share my screen. Give me a second. Evidently, I am a little bit tired. Okay. I'm very proud, basically, that we put together this great, fantastic group of speakers for all across the world, covering, as I said before, 11 time zones from Italy to Hawaii, 21 instructors. We provide 19 lecture and 18 application talks. And I am very proud to say that this is really an honor to have really the state of the art in every possible direction. And we will have in tomorrow also 2 virtual hands-on, one done here in Montevideo, and believe it or not, the other will be held in California. And this gives me the chance to pass to the next acknowledgement that I want to do is to, of course, David Jason and Enrico Graton. Both were a strong motivation for me across the year. I met with them in a workshop such as this in 2011 in Buenos Aires, organized by Susana Sanchez, by Valeria Levy, by Andres Gomez and Andrea Oliveira. And since then, they really changed all my perspective in my scientific career, but also in life. And acknowledge to Enrico, I will also like to acknowledge the LFD family, because we feel this like a family, and in particular the people who is in the other side in California, helping us with all the section, with the practical session in every single detail all the time. Finally, I would like to still and acknowledge that usually Enrico give after the close of the workshop, because I found this is really, really important, and I like it. I like it very lot. And he always like to acknowledge to the participant, and in particular to the student, because I absolutely agree with him that there is no such a workshop without the interest of the students. And I think this is very important to also be pleased. Finally, I would like to say that I will welcome all of you as many times as you want. This is a date for the next year on the 4th weeks of November. And I hope in the same place and the same time, we will have all of you again. So thank you very much. And if you don't mind, I would like to ask to all of you to turn on your cameras, so I will be able to take a picture of all of you again, as we did the first day. So I will wait a little bit for all of you to turn on the camera. Okay, give me a second. Okay, cheers. It will take me some time because I have several screens here. Okay. Now I go for the. Be careful, Belen. Okay.
No, I'm not driving. I'm at the back seat.
Okay.
Okay.
I will go in the second one. Okay. Wait a second. There. And let me see if I have another or I am done. Okay, I am done. Thank you very much.
Thank you. Thanks to everybody.
Excellent.
You guys, thank
So-
you.
Thank
Thank
you
you,
very much.
Lionel. Really, I mean, amazing course.
You. And we hope to, I hope to see you all next year, but next year I'm going to go to Uruguay, so I don't have to get up at 2 o'clock in the morning.
Yes, and for those of you who will come here, I will promise that we will celebrate Thanksgiving, but not with turkey. We will do an asado.
Right.
Even
It'll be
better.
a giant asado. Okay.
Okay, ciao.
Okay. Ciao, everybody.
Ciao, everyone. Great talk.
Bye.
Bye.
Thank you. See you, Matt. There.
Thank you, Lionel.
Thank you.
Great, Lionel.
Thank you, Lionel.
Okay.
Mañana seguimos.
Yeah.
No sé si
Are we all done, Lionel? Can I?
Yeah.
Okay, so I can have some lunch then, and well, maybe later tonight I'll get a Thanksgiving dinner. So
Okay.
thanks for all the effort.
Leo, te quiero pedir que me mantengas al tanto, porque yo me enteré de este curso por Dave, no por ti.
Okay, okay.
Chao, gracias. Descansa.
See you.
Sí, seguro.
Okay, so I'll see you tomorrow.
Okay, but can you stay a second? Just a second.
Yeah, I can hang out. I'm not doing anything here.
I just want to check something which is important for us is if we can have a split room and do the practical session. Unfortunately, Belen disconnected because the idea was to have at least one more or two more person.
Okay.
I can ask Alex to join again.
No worry, no worry. We will do it. Well, no, I need to test it today, honestly speaking, because Dave, if you need to go, don't worry. I
don't have to go. I'm sitting here all day doing nothing. So
Can you ask Alex, and I will ask Florencia if she can.
Yes,
Again, give me
I
a
can
second.
try. Yes, Alex.
time for my coffee break.